We're going to go over Chapter 5 here. Chapter 5 is kind of a lengthy chapter, so you might want to break it up into a couple days to give your brain some time to absorb the concepts, because it is, like I said, kind of long and don't want to run it all together. This chapter is all about the network layer of the OSI model. We've kind of moved down through the layers and we're at the network now. What you're going to see at this layer is that it's responsible for addressing the network, and it's also responsible for the route our packets take to get from one destination to the next. In this layer of the OSI model, we encapsulate the packet and we put the IP addresses on to that packet. What encapsulation means is basically we're adding information to the data. At the transport layer, we took that data and we made it into a segment. Here at the network layer, we're going to take that segment and we're going to turn it into a packet by adding our IP address information. When we get down to the data link layer, we're going to encapsulate that packet and we're going to turn it into a frame by adding MAC addresses. When we get down to the physical layer, we're going to take that frame and we're going to encapsulate it into bits. So encapsulation just means we're adding something to the data, where decapsulation means we're taking something off. So that's all encapsulation means. The video here, if you want to play that, it shows you a good representation of how that data goes from the segment to a packet to a frame and then to bits. The network layer, there are some applications that we're going to talk about again. The biggest one is IP version 4, the Internet Protocol. There are some other ones, IP version 6, which is the newest version of IP. We don't get into that a whole lot, but we talk about it a little. IPX, AppleTalk, and then the connectionless network service. TCP/IP is the protocol that was determined to be used on the internet, so that's why we hear about it the most often. IP addresses of our computers, that's where we get this term from the Internet Protocol version 4. IP is kind of like UDP that we talked about in the previous chapters. Like UDP, IP is connectionless, meaning that it doesn't make a connection, doesn't do that three-way handshake before we send our information. It's a best effort, unreliable type of delivery. There's no guarantee that's going to make it. Unreliable is kind of a bad term because more than likely that packet is going to make it through the network and get to where it wants to go. What we mean by unreliable is that it doesn't have a way to recover from errors if there is an error. If it does not receive all the packets, it does not have a way to resend those packets. But most of the time, it's not going to need to do that. It is media independent, means it operates independently of the media that is carrying all of the data. This slide here kind of relates connectionless communication with sending a letter and also with data networks. If you think about sending a letter to a friend, the sender doesn't know if the receiver is going to be at home or when they're going to receive that letter. They don't know when it's arrived. They don't know if that receiver is going to be able to read that letter, if they can read the handwriting or the language that you wrote it in. And vice versa, the receiver doesn't know when that letter is going to be coming. He doesn't know that you actually have sent a letter unless you called them in advance and let them know. Well, same thing can kind of be related to data networks and connectionless communication. The sender doesn't know if the packet is present, or the sender doesn't know if the receiver is present, if the packet has arrived, if the receiver can read that packet, and the receiver doesn't know when that packet is coming. Just kind of listens, and if something comes to it, goes ahead and takes a look at it. The IP packet has a smaller header, and what we kind of use the term as is overhead. The more information we have to add to a packet, the more overhead that packet has. So if you remember the TCP with the three-way handshake and the error correcting information, sequence numbers, acknowledgments, all that extra information that we had to add to make it a reliable type of protocol is called overhead, where IP does not have that. Again, it's just our best effort type of delivery. As I said before, IP is media independent, as are most other protocols. In the diagram there, it doesn't matter if we're going over copper Ethernet, copper serial, optical fiber, or wireless, that IP packet's going to be the same. It remains the same. That data inside of it does not change as we're going through different types of media. As I said before here, at the network layer we encapsulate the segment and we turn it into a packet. So the protocol data unit at the network layer is called a packet, whereas the protocol data unit at the transport layer, the layer right above the network, is called a segment. So what we do is we take that segment and we add the IP header to it, and now that is called a network layer encapsulation, and we now have a packet that is ready to be routed through our networks. When we send that information down to the data link layer, we'll encapsulate that packet, add some more information, and now that packet will be called a frame. So the protocol data unit at the data link layer is called a frame. This is what a IP version 4 packet header looks like. The ones that are in red over here on the right hand side, these are the more important ones that Cisco wants you to know about. The two most important ones that I think you should know about are the source address and destination address. These are going to be the source IP address and the destination IP address of who we're coming from and who we're going to. That's what we're adding in our packet when we encapsulate it, and that's a big part of it, who we're coming from and where we're trying to go to. This slide here just shows some other fields that are in the IP version 4 packet header. These ones aren't so important in Cisco's eyes, and I don't think they're that important that you remember them either. Like I said, the two main ones that I want you to know about are the source address and the destination address. The network layer gets into addressing our networks, and before we address our networks, we're going to want to have a way to divide up our networks. A large network is just going to be too complex, too cumbersome to work with. We're going to have poor performance. We're also going to have a little bit poor security as a result. So what we want to do is we want to divide up our networks. And in this chapter we talk about 3 ways how you can divide up your networks. The first one's geographic, and we'll talk about that in more detail in here in a little bit. Second way is purpose, and the third way is ownership. Okay, we can divide up our networks geographically, and this is what you're going to see a lot of the times. The reason is because all the wiring is going to be in a certain branch or whatever area of that office that you're working in. So let's say you have a company and they have a north office, a west office, and an east office. You just take all that information, all those computers, all of the servers, everything that's needed in those locations, and you would clump those together. If you think about the BSC campus, you'd have maybe Jack Science Center be one location, you would have Schaefer Hall be another location, maybe Werner Hall or the Armory be a different location. Again, the easiest way to do this is the easiest way to do it because all the wiring is in one building. We can do it by purpose. Here you might want to do it by departments. For example, they have the sales office. Well, salespeople need 100% reliability and speed, so you want to have that. You want to have all the salespeople linked together where you're going to have 100% reliability in your network. The art department down there, they need high bandwidth, so you want to put them maybe with your highest bandwidth out to the internet or whatever type of similar needs that they're going to need. You would group them together. Ownership With this ownership, you would group things on what you need. How do you need your files? How do you need your servers? How do you need your folders? In this example here, they have corporate records. Not everybody needs access to corporate records. Maybe only the supervisors or the bosses or something like that need access to those corporate records. So all the bosses, all the supervisors may be put into one group. Everybody else, just the normal employees or people who access their public website, wouldn't need access to the corporate records or wouldn't need access to all that important stuff. So maybe they would be grouped into a different type of container. Again, why do we want to separate our networks into smaller, more manageable things? Because we can have performance increases when we separate our networks. We can have better security for our networks, especially if we divide them up into ownership. And we can have better address management. What you're going to learn is that we're kind of running out of IP version 4 addresses. We want to conserve those as much as possible. And dividing up our networks is one of the ways we can do that. As we move towards IP version 6, that's not going to be much of a problem, but we're still using IP version 4, so that is still an issue. This is a packet tracer lab that you can do. This one should work just fine for you. This slide here is showing why we want to implement good security in our networks. Security is one of the biggest priorities of a lot of companies. There's a lot of hackers and viruses and things out there right now, and we want to have the appropriate tools in place and the appropriate setup of our networks so we can combat some of these security problems. Address management is another reason why we want to break up our networks. Hosts have the addresses for the other computers in their networks. Well, the more hosts that are on that network, the more addresses that we have to know. So if we break that network up, the less addresses that host has to know. If we want to get outside of our network, what we do is we send our information to a default gateway. Anytime we need to communicate outside of our local network, we have to have a default gateway. This slide relates an IP address to a street address that we might have as a person. It can all be broken down. This is called the hierarchical approach. For example, when we're talking about a street address, first we have to know which country we're in, then we know which zip code that tells us the city, then we must know the address. Once we're on that street address, we find the specific house or the specific building, and then we deliver to the specific person. Well, the same thing is true of IP addresses. For example, in this IP address, the first 3 octets, every set of digits is called an octet, and that's made up of 8 bits. And we'll see this in a future chapter here. When we go through submenu, it'll make a little bit more sense. But right now, just know that an IP address is hierarchical, and that's broken up into a network portion and into a host portion. So the first 3, in this particular IP address, the first 3 represent the network, and the last one represents the host. So when a router got this packet and it had the address of 192.168.18.57, that router knows that the network it needs to send to is the 192.168.18 network. Once it gets to that 192.168.18 network, it needs to find the specific host of number 57 and then send that information on to that host. Okay, here's the default gateway concept brought up again. Okay, if we take a look at that computer of 192.168.2.30, he says I only know the addresses of the devices in my network. So we could communicate with anything in the 192.168.2 network. So we could communicate with this computer here, the 192.168.2.31 just fine. He could communicate with a computer that had the address of 192.168.2.32 or 2.40. Anything in that 192.168.2 network, anything in that 192.168.2 network, he is going to be able to communicate with. If he wants to communicate outside of that network, he needs to send the information to the default gateway. And the default gateway is always going to be the closest interface of the closest router. And usually that's the fast Ethernet. So here's the closest router to the 192.168.2.30 computer, and the closest interface to him is this one. And that has an address of 192.168.2.1. It would not be this interface right here. That's not the closest one. It would not be over here on this router because that is not the closest router. So again, if we want to communicate outside of our local network, we send that information out to the default gateway. Same thing over here on this 192.168.3.0 network. That computer of 192.168.3.4 can communicate with any other computer that begins with 192.168.3. If it tries to communicate with something outside of the network, for example, if it tried to communicate with something over in here in the 192.168.2 network, what he would do is he would send that packet to his default gateway, and that default gateway would then forward it on to the other network. That's what this slide is showing you. If you go through the different steps there, the 1 through 6, this is showing you how that packet goes from one network to the next and how the routers take a look at that packet and decide where to send it next. So this is a good slide to go through those different steps and see how that packets get carried from end to end. So again, our gateway is going to be a way out of our network. If we take a look at our TCP/IP properties of our network connection on our computers, there is a spot for the default gateway. A lot of times we have our network cards to obtain an IP address automatically, so these would be left blank. But if you statically or manually set up your IP address information, you're going to have to enter a default gateway. So the address of this computer is 192.168.1.2. So he is in the 192.168.1 network. He can communicate with anything inside of that one network. When he wants to communicate outside of that network, for example, he wants to go to a web page, Google's on like a 64 dot something network, I believe. That's outside of our 192.168.10 network. What he will do is he will send that to the default gateway. If you want to check out what the default gateway of your computer is, you can go to the Start menu, Run, type in CMD and hit OK to go to your command prompt, do an IP config, and right here is your default gateway. So my default gateway is 165.234.62.1. My IP address is 165.234.62.34. So anytime I want to communicate outside of my 165.234.62 network, I will send that information to 165.234.62.1. This slide is just showing you what I showed you by doing the IP config. You can see your IP address, you can see your subnet mask, and we're going to learn about what a subnet mask is here in a future chapter. Basically what your subnet mask does determines what network you're on. And then your default gateway, again, that's how we get outside of our network. Outside of our local network, we send that information to the default gateway. Every single router has their own routing table. They're totally independent of any other routers on that network. So if we take a look at that local router on the left-hand side there, it has two networks that he can get to. He can get to the network 10.1.1.0 and 10.1.2.0. It specifies the next hop address of 192.168.1.2 for both of those. And if we take a look, that is the remote router's interface. So what we're saying is to get up to this 10.1.1.0 network, go to the next hop of this router. And once this router gets it, that network is directly connected, and you can go ahead and send it to the proper destination. Same thing happens with the 10.1.2.0 network. If we're at this router and we want to go to the 10.1.2.0, send it to the next hop of this router at 192.168.1.2. Once he receives it, he will be able to send it on to the correct destination because that network is directly connected. This picture here shows you what a real routing table looks like. If you ever go onto a router, you do the show IP route command. Don't expect you to know that now, but you'll do that a lot in semester 2. Do the show IP route command, and this is what your actual routing table looks like. So here, to get to the 10.1.1.0 network, again, which is right up here, go via 192.168.2.2, which means send it out your fast Ethernet to 192.168.2.2. How do I know we send it out the fast Ethernet? It says right here. So again, to get to the 10.1.1.0, send it out your fast Ethernet to this next hop. Let that next router go ahead and deal with it. Our computers also have routes to places on our network. We're not going to talk a whole lot about this, but if you ever want to check out what the routes that your computer has, you can go to the command prompt and type in netstat-r, and that will show you the routes that your computer has. This is taking a look at the routing table here a little bit more in depth. The first part of it, the 10.1.1.0, 10.1.2.0, and 192.168.1.0. These are specifying networks that we can get to. We don't specify specific computers, we specify whole subnets. So anything in the 10.1.1.0 could be 10.1.1.200, 10.1.1.2, anything in that 10.1.1, this is how we get there, via 192.168.2.2, which is to send out our fast Ethernet. So this current router here can get to 3 different networks, and that's it. I just got done saying that this router can get to 3 different networks. What if it got a packet intended for the 26.2.1 network? How would it get there? Well, it did not have a route to that, so what it would do is it would drop that packet. If it doesn't have a route to it, it will drop it. One thing that we can add in there so it does not drop that packet is to add a default route or a gateway of last resort. Default route and gateway of last resort are the same thing. What the default route does is it says anything that I do not know about in my routing table, send to a specific address or send to a next hop. And that's denoted by the quad 0. So what we have here is a gateway of last resort of 0, 0, 0, 0, which means anything I do not know about. So anything that's not in the 10.1.1.0, anything that's not in the 10.1.2.0, or anything that's not in the 192.168.1.0, what should I do with it? Instead of dropping the packet, send it to the next hop of 192.168.2.2. This line here and this line here basically showing you the same thing. So anything I do not know about in my routing table, go ahead and send it to my gateway of last resort. The next hop is where we're supposed to go next. If I do not have a next hop, it's going to be directly connected, usually to a fast Ethernet or to a serial. If I do have a next hop in here, for example, is 192.168.2.2, we have to perform a recursive lookup and figure out what interface we have to send that out. Well, we already did that recursive lookup, and we figured out to get to the 192.168.2.2, we send that out our fast Ethernet. So that's how we did our recursive lookup. Said, how do we get to here? We get to there by sending out our fast Ethernet. So our next hop just means which router do we go to next. This slide here is kind of showing how our router takes a look at the information. Here a router gets a packet for the data network of 10.1.2.0. So what the router does, it removes the layer 2 encapsulation. We take off anything from layer 2. We haven't really talked about layer 2 yet, but we remove that type of encapsulation. Then the router extracts the destination IP address. We want to see where we're going. We're trying to get to that 10.1.2.0 network. Then the router checks the routing table for a match, and we did have that 10.1.2.0 in our routing table. So that network is going to be found. We re-encapsulate the packet, and we go ahead and we send it on to the destination that was in our routing table. In this example here, we're trying to get to the 172.16.2.0. Again, the router removes the layer 2 encapsulation. It extracts the IP address. We're trying to get to 172.16.2.0. Router checks the routing table for a match. The network 172.16.2.0 is not in that routing table, but we do have a default route that exists. So the router re-encapsulates that packet and goes and sends it to that gateway of last resort of 192.168.1.2. That router would get it and repeat this process over and see if he has a route to the 172.16.2.0. If he does, he would send the information on to the correct destination. If he does not, he would drop the packet. If he does not, but there is a gateway of last resort for him, he would forward it on to his gateway of last resort. This is what happens here when there's no match in the routing table and there is no gateway of last resort. Get that packet, takes a look at it to see if there is a route to it in the routing table. If there is not, and if there is not a gateway of last resort, we discard it, get rid of it. This slide here is just showing you that each router has its own independent routing table. They're going to use only the information in their routing table. What we'll learn is there's a few different ways we can add routes to a routing table, and one of them is dynamically. And with a routing protocol such as RIP, each router exchanges their routing table information. They exchange their complete routing table, and in that way they can kind of use the other routers' information on how to get to a network. But for right now, just think to yourself that routers only use stuff in their routing table. One of the ways you can add routes into a routing table is statically, meaning that the administrator has to do it manually. We manually type in which route we want to get to, or which network we want to get to, the subnet mask, and then how do we get there. So here on router A, let's say we wanted to get to the 10.1.1.0 network. What we would do is we'd go to router A and we would say IP route, well, this is the command you would type in, IP route 10.1.1.0, that's the network we're trying to get to, subnet mask of 22255 and a 0. How do I get to the 10.1.1.0 network from router A? I send it to the next hop of 192.168.2.2. Or I could say send it out this fast Ethernet. Most of the time you probably enter in that next hop. B would take a look at that packet then, and then he would see if he had a route to the 10.1.1.0 network. If he did, he'd probably send it on to this next hop. So with our static routes, we have to enter them in manually. And it's usually only good for small unchanging networks. With dynamic routing protocols, such as RIP, EIGRP, OSPF, we have to just do initial configuration, and then all the routes get exchanged with one another. So router A would get all the routes from B, and it would also get all the routes from C. So they all share routes to each other. Instead of having to statically or manually enter in those routes, it will fill in all that information for us. We usually want to use dynamic routes in larger changing networks. In this packet tracer example, you can see how these dynamic routing protocols exchange their updates. That is it for Chapter 5. You will not be able to do this hands-on examining the device's gateway because you do not have the server set up and the whole topology that is set up. But you should be able to take a look at the diagram inside of this and see which devices would have what for default gateway. So you can take a look at it, but you won't be able to do it fully. You can do it through the packet tracer. You do it through the packet tracer, but you can't do the previous one there, the hands-on. Examining a route. Here you won't be able to do this one because this wants you to be on an actual router. But you will be able to do it in packet tracer, so I encourage you to take a look at this one. Alright, that's the end of Chapter 5. This slide here is just a little bit of a summary. If you have any questions about anything that I've talked about or anything in the reading, please feel free to contact me, email, call me, or stop by my office and I can help you out. Thanks.